So we know that there are three primary states of matter: solid, liquid and gas. We also know that I can go from one state of matter to the other state of matter by changing the pressure and temperature. So this particular fact is represented by something known as phase diagrams, where we plot temperature on one axis, typically the x-axis, and the pressure on the other axis, typically the y-axis. So that is the increasing pressure and increasing temperature. Another thing about the phase diagram is that instead of calling them states, we actually call them the solid phase, the liquid phase and the gas phase. This is the phase diagram for water. Now there are several important things that we can understand from this phase diagram. Let's first understand how to actually read this diagram. So we pick a particular pressure. In this case, we pick the pressure for 1 atmosphere. So this is the normal atmospheric pressure line in the phase diagram. That is what I have picked from here. And we pick a particular temperature. So 0 degrees Celsius, let's just pick that. And at the intersection of these two lines, I can now understand from the diagram what would be the state of water. In the case of water, we know that at 0 degrees Celsius normal atmospheric pressure, the solid water would start turning into liquid, and that is what this diagram is also representing. If I increase the temperature a little bit more, I know that at our normal atmospheric pressure, the water would start boiling at the temperature of 100 degrees Celsius, and it would start slowly and gradually moving towards the gas phase. Okay, so at 100 degrees Celsius, we know that the liquid water would boil at normal atmospheric pressure and it would be converted into gas phase. So that is how we read this diagram. That is the first thing. The second interesting aspect of these diagrams are these lines. These lines represent the phase transition point, where one phase of that particular material, in this case water, is transitioning to the other phase. So if you notice, these particular lines also give us these particular phase transition boundaries also give us a lot of information. For example, in the case of water, I know that the boiling point for water at 1 atmospheric pressure is 100 degrees Celsius. Now what happens if I increase the pressure? As I increase the pressure, so pressure is increasing, this particular diagram is telling me that the boiling point also increases. So the liquid to gas transition at higher pressure would happen at higher temperature. This is what this diagram is telling me. So for example, if I read, if I go up in pressure, so this is higher pressure. As I go up in pressure, my boiling point, if I want to read it from the x-axis, would also increase. And this fact, of course, we use in the pressure cooker, where we force the water to be in higher pressure state, thereby increasing its boiling point. And because of the higher boiling point, there is higher temperature. The food cooks at higher temperature in the case of pressure cooker, and therefore it cooks at a faster speed. So that is what the second important thing about these phase diagrams. Now, why is there a tendency? Why do I have to provide more energy to water to make it boil at higher pressure? See, as the pressure increases, the tendency of the substance to remain in lower volume state, right? So liquid water has lower volume than gaseous water. The gas has, of course, water vapor has a higher volume. So as I increase the pressure, it takes more and more energy to break the bonds forming the liquid water, to free the liquid molecules into the gaseous state, because the bonds, they become tighter and tighter due to the higher pressure. I am exerting more pressure. I am forcing those molecules to remain together more and more, and therefore I would expect that I would have to provide more energy. I would have to increase the temperature further to go from the liquid to gas state, right? That is what to be expected. Now the same thing is to be expected even in the case of solid to liquid transition, because as I increase the pressure, there should be an increased tendency of the solid ice to remain solid, and I should be providing more and more energy to it to convert into liquid. So this solid to liquid curve, I would have expected it to go like this, but it doesn't go like this. It actually goes like this. Okay, so it goes in the reverse direction. It does not go like this. Okay, it goes in reverse direction. And why is that? In the case of water, this is an exception, Because liquid water near its melting point has a lower volume than solid water. So as I increase the pressure, there is more and more tendency of the liquid of water to remain in liquid state, because it has lower and lower volume, than the solid phase, and therefore the melting point of the water actually decreases with increase in pressure. So as I increase the pressure, there is a decrease in melting point rather than an increase, because the liquid water has a lower volume near the melting point. Okay, so this was the case of water. This is a normal phase diagram, and in the case of a normal phase diagram, this is what we have shown. Okay, this is the normal line. Okay, and as we had expected, this curves in the same way as we had expected. So as this is not for water. This is for any other substance, and the liquid to solid. Right. So this is the solid, and this is the liquid phase. The transition line between solid to liquid has the correct slope as we would have expected. Now, other 2 points in that I want to show you in using this particular phase diagram are the triple point and the critical point. So, triple point is the point on the phase diagram, is particular temperature and pressure at which all the 3 phases, the solid, the liquid and the gas phase of the substance, can coexist together. So they are all there at this particular temperature and pressure. They are all there, and they are all at equilibrium. I can go from one to the other. The next important point is known as critical point. At the critical point, that means that at the critical pressure and critical temperature, this particular pressure and temperature, the 2 separate liquid and gaseous phases, they become one, which is known as supercritical fluid. Now, another way to look at this critical point is that if I increase the temperature above the critical temperature, I really cannot go from this supercritical fluid state to the liquid state just by decreasing the pressure. If I decrease the pressure from after the critical temperature, if I decrease the pressure of the supercritical fluid, I would get the gaseous phase, but I would not really get the liquid phase. To get to the liquid phase, I would necessarily have to lower my temperature below the critical temperature. So that's another definition for critical temperature. Critical temperature is the temperature after which the liquid phase of the matter does not really exist at any pressure, no matter what your pressure be. Okay, so with this we have understood everything about the phase diagrams, how to read the diagrams, what are the important points on the diagram, and of course about the phase transition lines and what do they tell us. If you have any questions or other interesting things you want to put down about these phase diagrams, put them in the comment section below, and we'll be very happy to include those. Thank you.